All right, we'll go ahead and get started. Today we'll be exploring SOLIDWORKS Flow Simulation and how best to analyze all electric designs. My name is Enrique Garcia, and I'm a Senior Applications Engineer here at GoEngineer specializing in our simulation products. This will be the last part of a three-part presentation series that will explore various capabilities of SOLIDWORKS Flow Simulation. If you've joined us for the last two presentations, well, welcome back, friends, and welcome to any newcomers as well. Before we review the final agenda for today, here's that general slide showing how SOLIDWORKS Flow Simulation is offered. So there will be some tools that we'll be using that only are available in our HVAC and or electronics cooling modules. We've covered this slide a few times already, so please let me or anyone here at GoEngineer know if you have any questions about pricing or capabilities. So here's the agenda or roadmap for our webinar series. We've done the first two webinars, and today we'll start with our last webinar by continuing on with our setup from yesterday's webinar. And we'll focus on the accuracy of our heat transfer and thermal output with our established project, and we'll add some special features that will be incorporated in our workflow. Also, before we start, if you have to leave the session early, we'll be recording this webinar and we'll be posting it to our GoEngineer YouTube channel after a few days. Also, if you have any questions while I'm presenting, feel free to ask, and if there are no technical issues on my end, I'll be able to see your questions and answer them as I go along. Also, as always, I'll have some dedicated time at the end of the presentation for final questions. So yesterday we set up our simple electronics box in SOLIDWORKS Flow Simulation with conditions that represented the operation of our device in the hottest place on Earth. And we confirmed that the temperature of our integrated circuits under the two heat sinks here struggled, or at least began to struggle for this new environment, as we quickly reached or exceeded the operational limit of the integrated circuits of about 92 degrees Celsius. So as shown on this slide here, we tried maximizing the performance of our components by introducing a second fan. And to help along the accuracy of the project, we also extended the computational domain of the surrounding fluid medium. This did help a bit lowering our temperatures slightly, but we saw that this type of change was definitely in the right direction, and so we'll focus on the accuracy of our setup and continue to adjust our study by replacing a few of our existing features with new ones. This process will give us better accuracy of our heat transfer model and a more definitive verdict of our performance of our two integrated circuits. So let's go on back to our SOLIDWORKS screen and let's set up our project with these new conditions. All right, so we're going to be continuing on with our previous project from yesterday that will include the external analysis aspect of the project. And like we mentioned just now, we're going to be looking at adding more accuracy to the design. So the first thing we're going to do is we want to test to see if that radiation model, or if radiation even plays a role in the energy transfer of our two integrated circuits. So the first thing here for this particular external analysis with the two fans, let's go ahead and look at the goal plots and let's kind of remember what those values were before we continue on and do our comparison. So let's jump in here and let's click show. And so if you recall, our operational limit for these ICs are 92 degrees Celsius. And so it looks like we're just passing our requirement limit for one at about 90 degrees Celsius and failing for the other at about 95 or 96 degrees Celsius. So we'll keep that in mind for our comparison here in a moment. So next, let's clone this project, and we're going to turn off all of our radiation aspects of this design. So we'll come up to this external part, two fans, and let's clone the project. And let's name this one External No Radiation. Two fans. All right, let's create the new project. And we're editing the general settings here to exclude the aspect of radiation here. All we're doing is we're just unchecking the radiation component from the physical features section. Click apply. OK. And at this point, again, we would run the project. And so I have already pre-run these projects for us. So let's now take a look at that no radiation project. And let's edit the goal plot and compare our results. So again, we were at 90 and about 95, 96 before. So let's go to our goal plot here and take a look to see if radiation truly matters for our ICs. And so we can pretty much see here that the results are pretty much the same for the two ICs, so with and without radiation. So that's just a good thing to know about those components. We're not saying that for any of the other components, but at least for the ones that we were sensitive to, the radiation model doesn't seem to play a factor here. We can also take a look at some of the cut plots. Zoom that out here a bit. So we can see that in the previous project with radiation, we had in the cut plots, we had additional details showing the maybe surface to ambient heat transfer that is most likely due to the radiation in the flow fields as compared to the current one we see here that only shows the ambient temperature, surrounding temperature there of about 56 degrees Celsius. Now, this particular model of radiation that we have just used can be used in general or for perhaps a preliminary study, but it's not ideal for an electronics box heat transfer situation like we have here. The official simulation documentation recommends that this discrete transfer radiation model be more for modeling more compact radiation sources like an incandescent lamp or light or a furnace with maybe extremely high temperatures. So moving forward here, the decision will be to keep radiation on, in this case, just to make the overall model more accurate, but we'll actually use another more applicable radiation model that comes with the HVAC module in Flow Simulation. Although we're not reviewing results for the other components necessarily in our project, this mechanism of heat transfer could be important for future investigation of those components, and so we'll use the more applicable radiation model here next. Let's go back to the external part with the radiation model turned on, and let's now copy or clone that particular project to use that as a baseline for adjusting our radiation model. Let's go ahead and call this one part 3. And the first thing we're going to do is change the general settings and update our radiation model. So let's go in and click on General Settings. And under radiation, let's expand that section and let's change the model there from discrete transfer over to discrete ordnance. So although we verify that radiation won't impact the temperatures of our ICs, for us this radiation model will be the preferred model for electronics cooling in general, as it's more accurate with lower temperatures and models without a compact or concentrated radiation source. So this particular radiation model is available exclusively in the HVAC module. In the previous webinar, we used the discrete transfer radiation model, which again comes in all versions of flow simulation, which is more applicable with, again, much higher temperatures of over 160 degrees Celsius or about 1300 Fahrenheit, and again is better with a concentrated radiation source like a space heater or incandescent light or something like that. So with this radiation model, we need to also click the absorption in solids checkbox here to consider radiation absorption in our other solid bodies. So again, we're making sure that that's turned on. So with the discrete ordnance radiation model, the absorption coefficient that's referred to here can be specified in the solid material definition in the engineering database, or you could also have a list of radiative surfaces on important components, which can be applied locally for both radiation models as a radiative surface feature. So we'll do that part here next on a few key components. Let's click Apply, and OK to close the general settings. So moving forward, I'm going to switch over to my Part 3 completed project and review the setup this way. It'll be a little more efficient to go through the rest of the setup. Now, the new aspect here for this project is going to be assigning those radiative surfaces or features in the model, and that exists here in our tree. And so just to step through them, we've assigned 3 just as the majority of the radiative surfaces here of our project. So I want to go in and look at my first one where the idea is you pick the different components. In this case, we pick the two heat sinks, the large capacitor, and the four medium capacitors. And then below under type, we can specify from a list of established real surfaces that, again, comes part of the engineering database. And so we've gone in and we've picked real surfaces, and we've picked aluminum in this case. Let me back out here. So we picked, again, aluminum rough in this case. So we went ahead and did that to some of the other key components. We also did that with the copper to transformers. We clicked and picked a copper polished type of real surface for that. And then lastly, for the components that make up the housing of the model, we went and picked a black matte shellac surfacing for the two sides and then the top and bottom, including that hidden top of the housing of the component. Let's close that out. So again, we have our solar radiation and our thermal radiation more accurately modeled now in our system. If we had other sources of radiation that needed to be introduced, such as a very strong light source or other significant heat source like a heater of some sort, we could do a radiation sources feature for that and just include those features in the flow simulation design tree. So these radiation sources are meant to introduce additional radiation energy that maybe isn't part of the model under investigation, but can be put into the computational domain as a simplified shape. An example of this could be, again, a strong light source or furnace operating next to your electronics enclosure that can be specified as maybe a box or a cube that you model in SOLIDWORKS and incorporate into the flow project. For us, since we don't have anything like this right now, we'll go ahead and close this and just continue on without this feature. Next, we'll redefine our two integrated circuit heat sources with a more accurate two resistor component feature. So this feature is a model that is available with our electronics cooling module only and represents the heat transfer of an electronic device with small electronic packages such as our two ICs here. So for that, you're going to notice that under our heat sources, we've gone in and we've removed our volume heat sources for the ICs. We have all the other ones left intact, but we've deleted that to make room and to replace it with this two resistor component model. Also, if you look here under our solid materials, under our silicon, we've removed the two or the bodies that constitutes the four IC bodies references from this feature as well. We're going to be specifying this with a two resistor component model. So after we've removed, again, the solid material aspect of it, the heat source material aspect of it, both of those are going to be incorporated down below here under a new feature called two resistor components. So let me go in and just walk you through how I set this thing up. So before assigning anything, I selected the standard chip array, the 19 by 19 millimeter line item from the predefined list of components that, again, these are all included in the electronics cooling module here. So at that point, I applied our 2.5 watt heat source down below. And for our temperature, I just put in our room temperature here since it's only an initial temperature. Then above, in the second fill-in field here, I selected our either a single component, or in this case, we have two individual components that make up the first IC. So this will automatically set the top face reference for our two resistor component feature you see here in blue, in the blue fill-in field for the top face. And before we move on, I just wanted to point out that we can probably expect that our temperatures for our ICs now will be a little bit higher than when we use the volume heat source definitions. So we can explain this since the two resistor component model represents highly complex geometry versus when we just applied a volume heat source to the entire volume of the IC, which is more simplified. So this two resistor model feature will actually calculate three different temperatures at different heights of each of the ICs. One for the case node at the top of the package, one for the junction node in the middle of the package, and then one for the board in the area that makes contact with the PCB. Also, just to note, the temperature that will be recorded for the junction value will be the highest temperature in this whole two-resistor component model. So here we have a feature that will calculate 3 separate temperatures for the area versus the volume goal for a regular volume heat source will only calculate 1 temperature and that's it. Also, before we move on, another big contributor to this expected temperature increase here will be due to the fact that the sidewalls of the ICs here now will be now considered insulated or adiabatic. So heat energy can only spread from the package top or bottom and not from the sides like before. All right, let's go ahead and close this out and let's talk about the actual PCB as well as one of our other features we can manage. So if you look here in my flow simulation design tree, you'll notice that the solid materials feature for that FR4 material for the PCB is no longer there. We went ahead and deleted that, and we're going to replace it with something called the PCB generator, or printed circuit boards generator. This is another feature that is exclusive to the electronics cooling module and flow simulation. So let's go in there and take a look at how this thing is applied. Again, it's a very similar workflow. So we go in, we select a body, and then we select the idealized or the actual electronics cooling module from the database. So for this thing to work, for this feature to work, the PCB geometry needs to be thin in one direction, like it is here, with 2 pairs of parallel faces. So a basic or standard PCB shape. Otherwise, this is not going to work. So this is how the feature determines its direction due to our anisotropic properties of our PCBs. So we'll pick the predefined PCB item here that has a 2 signal layers and a 2 power layers section, the default. Or we can also create our own PCBs from the engineering database. I can click on this button here to open up the database. And we can see if I go in under properties, I can enter some of the properties of the PCB. And more specifically, if I go into this Tables and Curves tab, I can specify each individual layer in terms of layer thickness, and then on the other column, the percentage cover of the conductive material in each individual layer. Let me close this out, and that's how we assign a printed circuit board feature to our PCB components. So that about covers all we can upgrade for this particular model for the moment. So at this point, I would run this project. So let's open up the already run analysis and let's take a look at some of the results. So for us, we're going to scroll down. These have already been run. And the first thing I want to do is turn on my surface plot and let's take a look at my goal plots as well. And let's go to our goal plots and let's take a look at what we have for our goal plots for our 2 ICs. So we can see that our IC temperatures here are much greater now, and they reflect the result values of a more accurate setup due to the electronics cooling module. So the temperatures for the ICs now in the maximum column are about 112 and 121 degrees Celsius. Again, super toasty. We stand no chance with this type of forced convection cooling, right? If I were tackling this project in real life, we would probably have to reconsider the whole cooling design if we plan on running this electronics box in these harsh environment conditions, right? So we can see here that the 2 transformer components are pretty much blocking the airflow to that rightmost heatsink, just to start. So let me close this out. And the last item I want to review with you here is the idea that instead of heating our regions of a model with maybe a volumetric heat source or surface sources, we can also consider joule heating areas with an electric current or a voltage. This capability is once again exclusive for our electronics cooling module. For this, I'm going to go ahead and transition to another component or a simplified example I want to show here just in closing for our presentation. And so for this, we're gonna be focusing on this already completed project just to show this joule heating functionality. We'll be reviewing inputting realistic currents into the model or along the traces of our PCB here, and these will generate the equivalent heat energy due to this type of heat loading. So let me go ahead and edit one of these electrical sources features here in the design tree, and that's really key for our joule heating functionality. And let me zoom in here to the area of interest. So we can see here that we've specified the type of electrical input on the left-hand side, on the top under type, whether that's a DC current, as it is in this case, or we can also do a voltage, a DC voltage. Then we specify the input phase from the graphics area just to populate the fill-in field and show the radio button below to specify this as an input. And then we gave it a 1 amp magnitude. So now let's go ahead and take a look at the second electrical source feature here in the list. So we can see that we've also chosen the DC current source type over on the type area. And we've selected the downward end face here on the trace of this PCB for the selection box, the one that was closer to the IC package. It's right over here. And then down on the property manager, down below there, we've picked the out radio button this time and entered that same 1 amp magnitude as before. So let me close that out. And so that's the pattern I've taken for each of the trace geometries in this model. And I went around the entire geometry and all the set of traces in the same exact way with all the current features you see here on the flow simulation design tree over to the left here. And so we've created a separate input features and separate output current electrical source features for each of these traces. So again, and then as far as the geometry of the traces, they are actual solid bodies that we've modeled into the PCB. And as far as the rest of the setup for this project, let's take a look here. I've assigned copper just to all the traces in the solid materials folder. We did a PCB generator feature like we did in the previous project to the PCB model. And also we did a similar 2 resistor component model feature to the IC here. So let's take a look at the results here. I went ahead and let's load the results. Let's take a look at some of the cut plots that I've made here and some of the surface plots in the results set. Let's go and let's look at the existing cut plots. And let's go ahead and show the surface plots both on the board and on the traces themselves. So here we can see how we're heating up. We can see qualitatively what's going on. And we can take a look at the traces themselves, how they're heating up as well, if we kind of isolate those individually. And lastly, let's take a look at a goal plot here. I've made a goal plot of all the engineering goals that are important for this model. More specifically, let's go in and examine the calculated temperatures for the case temp, the junction, and the board temperatures here of the IC package. So once again, under goal plot here, I can say edit definition. And I've chosen those 3 nodes that are calculated. Those can be selected under the parameters section of the engineering goals. And so these are my temperatures that we see here for that particular model or IC in these conditions. So that was our last presentation for the series here. So before we end with any questions, one last time I just wanted to promote our dedicated GoEngineer YouTube channel. We post videos here very regularly, and we invite you all to subscribe and stay up to date with our latest uploads. We have a wide range of topics here that are covered, including simulation, so definitely feel free to check us out on YouTube. Here's our slide showing that we also produce a blog on our website that's very active with many tips and articles with useful information regarding SOLIDWORKS, simulation, and many other technical topics as well as fun projects our engineers have been doing with 3D printing and scanning, to name a few things that we do. All right. Well, with that being said, I'll stay on for a few minutes here to help answer any lingering questions you may have. But again, thank you again for attending my presentation series this week and last week, and we'll see you on the next one.